This is it, the moment I've all been waiting for, the deepest of deep dives ever into nuts and bolts and doing them up and all of that related hands-on crap. I'm talking the Marianas Trench of deep dives into this. I'm John Cadogan from AutoExpert.com.au and I get new cars cheap for buyers here in Australia. Website for that, obviously, or you can just click the card that's up there now, dude. Okay, so a week ago, whatever it was, it's all a blur on lockdown, but about that length of time, you might recall a dude named Neville No Name presented with a loose tow bar, and AFD, or arsehole Ford dealer, didn't do the bolts up properly to start with because they're loose, and that's the only way they could have conceivably come loose. And P.S., the chassis is also cracked. And I did a follow-up on that, and then tsunami of commentary from you about better go out and check my tow bar. What if it's loose too? What if the chassis is cracking? What if those bolts are imminently to fall off? See, in the domain of good and bad, I would categorise tow bar just falling down onto the road. I'd put that firmly in the domain of bad. I really would, especially seeing as the safety chains, which are, let's face it, designed to restrain a runaway trailer, are also inconveniently bolted to the tow bar. So this whole restraint countermeasure sort of hinges on the tow bar remaining attached to the car. And I can just imagine all of these dudes, people who didn't comment, and dudettes, let's not forget, because this is a non-gender specific implement, rushing out, grabbing the tools and checking those bolts. And I'd suggest that this is the wrong way to do that, because I see this all the time, right? All these people are going to cut stuff up or nail stuff together or drill holes in stuff, and they reach for the tools first and they forget to engage the most important muscle of all, okay? So let us do that first and then go out and make sure our tow bars are still attached, all right? And up front, I'd say it's not a bad idea to make sure that the vehicle is adequately restrained, like handbrake on, in park or in gear with a wheel chock in place before sticking yourself under it. But it's not a bad idea to get under there with something from my very good friends at Olight and just have a look around, see if anything's loose or leaking or there's any evidence of anything imminently to go poopy in its trousers. It's not a bad idea to get you to know your car intimately down there. Know what I mean? Anyway, so you can give the tow bar bolts a visual inspection. You can even put a wrench on them and just make sure they haven't come loose, like if they're finger tight or not snugged up. That's nature telling you that you've just averted disaster, right? But if you want to do them back up, this is where everything sounds simple, but it's not really, okay? Like, everything sounds simple until you do it. So here's what I would suggest about all of that. And I've just been out and had a look at the mighty Triton. There's no evidence that the bolts there on the tow bar, which were fitted by the dealer, there's no evidence that they're loose or malfunctioning in any way. There's no evidence that they're moving. There's no visual play, none of that stuff. So apparently all good. But it does have lock washers. And lock washers or spring washers, that's one of the first things I want to address here. We did talk about that in the last video on bolts, but I want to go there again because I got a fascinating resource sent to me by one of you, a dude named Mike Cochrane. And Mike is a engineer on the railways in the old Dart, in the United Kingdom. So he sent me this fantastic resource, which is essentially, there's the cover. It's from NASA. It's called Fastener Design Manual. Now, I have put a link to Fastener Design Manual and also another really useful resource that any of you bolt tightening apprentices would like to use. It's a fantastic reference. It's the Ajax Fastener Handbook. Now, if anyone knows anything about bolts, it's Ajax, and I'd suggest NASA's probably pretty good on this front as well. We'll get to Ajax in just a minute, but on the lock washer front, just in case you're harbouring any lingering doubt about lock washers, last video I said don't worry about them, completely ineffective in high tensile joints. I'm going to read a quote directly from that manual that you can download, and it is a bit of an insomnia cure, but also very interesting if you're into this stuff. NASA says, the typical helical spring washer is made of slightly trapezoidal wire formed into a helix of one coil, so that the free height is approximately twice the thickness of the washer cross-section. They're usually made of hardened carbon steel, but they can also be available in aluminium, silicon, bronze, phosphor bronze, stainless steel, and K-monool. The lock washer serves as a spring while the bolt is being tightened. However, the washer is normally flat by the time the bolt is fully torqued. At this time, it is equivalent to a solid flat washer, and its locking ability is non-existent. Now, just for complete disambiguation here, NASA concludes with this sentence. They say, in summary, a lock washer of this type is useless for locking. So I think we can put the whole lock washer thing firmly to bed, don't you? There are 18 lock washers on the mighty Triton tow bar, all of them uselessly doing their job. Yes! So there's that, okay? Now, just to go back to basics on this, so you know exactly where we're coming from, okay? This is what happens when you stretch a bolt by tightening it up. And that's what happens, okay? You stretch the bolt, and by virtue of its stretching, it provides clamping force on the parts. This makes perfect sense. You cannot have one without the other. The stretch is not visible to the naked eye. I mean, obviously, the longer the bolt, the more it stretches to provide the equivalent clamping force, but you're not about to see it, okay? It's the kind of thing you can really only measure with precision instruments. But here's what's happening down there in the thousandths of an inch micron sort of domain. You've got stretch here and you've got load here. And obviously the thread on a bolt, stand by. Here's one I didn't prepare earlier, but the thread on a bolt, it's just a big long ramp wrapped around a shaft, and it's got a particular pitch, like the steepness of the ramp is defined by the manufacturing process of the thread. And as you push against the part, let's say this other nut is the part, when you push up against it and start tightening, the ramp just, it's like driving a wedge into the handle of a hammer or any other operation like that involving a ramp, you know, building the pyramids or something, then it just clamps, okay? And you know how much the clamping is going to be, because a typical fastener for things like tow bars and wheel nuts would be M12 by 1.75, the 1.75 being the distance between the peaks of the threads in millimetres, okay? That's just how this works. So the amount of stretch gives you clamping force, okay? Any suggestion that there's no stretch or some bolts are designed to stretch more, I mean, some bolts probably are designed to stretch a little bit more, but the stretching loading relationship is defined by the metal, okay, the material properties of the metal and its physical size, its heat treatment, things of that nature, okay? It more correctly, strain and stress, or stress and strain, okay? But just think about it like stretch of the bolt, like how much it elongates as you tighten it up, and the amount of clamping force or load that is inside the shaft of the bolt by virtue of you torquing it up. That's how this works. And if you just do this with an infinitely strong torque wrench or something, you put a dirty, big lever arm thing, much more significant than that, on it, and you just crank it till it breaks, it goes through a bunch of landmarks on the road to Fracture City, okay? So it operates elastically in this region here up to a thing called the yield point. And the yield point is literally the boundary between elasticity and plasticity. The difference being when you take the load off, it goes back to its original size and shape below the yield point. After that, it unloads a little bit elastically, but it remains stretched or permanently deformed, okay, over here in the plastic region. And that's why you've got to throw these torque to yield bolts away, you know, because they go past the yield point, the deflection gets plastic, and you can't use them again because they don't tighten up the same way again. But here's what happens, okay? You go past the yield point and then you get more and more stretch in this plastic region, and you get more and more clamping force as a result. Okay, and that's why they use those torque to yield bolts. But ultimately you get to this thing here called the ultimate tensile strength. And if you keep the load on after that, or if you keep applying torque after that, then the fracture becomes a foregone conclusion. It just runs away because even less load now, you got lower load, but you get even more extension. And if you do this in a test rig, what you see is part of the sample that you're breaking to destruction just starts to what they call neck. It reduces in its diameter in this region here. The failure becomes a runaway train, and it just goes bang by the time it gets here at a much lower load than the ultimate tensile strength. I'd suggest it's vitally important that you take responsibility for this stuff, because if you go out there and you take bolts like this and you overstretch them, then you will reduce their strength over time, and that could have dire consequences. And that's why we need to be entirely conservative when we deal with all of these kinds of phenomena, okay? And there's a whole process in place that is designed to make this safe, all right? So let's talk about being conservative and having factors of safety in play. So the first thing you need to know about bolts is there's this thing you'll see in tables all the time called the proof load. And essentially the proof load is quite arbitrary. It's about 2/3 of the yield point, 65%, let's say. So whatever the number is for the yield point, you knock a third off and you're at this thing called the proof load. And if you just operate the bolt by stretching it up to the proof load and not going further than that, then you can more or less assemble, disassemble, reassemble, repeat indefinitely without any implications for the longevity of the fastener, okay? It's infinitely durable if you stay below there. Infinitely is a big word, I mean in practice, okay? Nothing lasts forever, obviously. And then what they've done there is, how do you get there and how do you stay below here? Or when you get something like the Ajax Fastener Handbook, it will give you the recommended assembly torques for these fasteners, provided you identify them correctly, okay? And the assembly torque is between 2/3 and 3/4 of the proof load. So you're talking about 70% of 60-something%, which is kind of just on the shy side of half of the yield point. So if you get this right, even if you botch it a little bit, you're still conservatively below the yield point, and the fastener is going to be sufficiently tight that it will not come loose in normal operation. That's the other factor, right? This assembly torque is kind of the sweet spot, right, between vibrating loose and failing in service from fatigue or whatever. In fact, it's much easier to fail in fatigue if you don't do it up tight enough, okay, because it'll come loose, and cyclic loads on the mechanism, whatever you're joining together, can lead to a fatigue failure far more often than if you just tighten it up properly. So it's not safe at all to under-tighten bolts. It's certainly not safe to go over here either. So you've got to get in this red sweet spot area. You have to do it. You have to take responsibility, particularly as assembly practices inside dealerships, particularly for things like accessories, tow bars and things of that nature, are poor often enough to worry about, okay? So if you wondered what all of the numbers mean, you can look at the head of a bolt. This one's got, I don't know if you can see that, but I'll try and get, there you go. If you look at that, you can see that it's got 8.8, hopefully. And if you can't see it, because I can't tell, you'll just have to take my word for it. It says 8.8. And this is because it is an entry-level high tensile fastener called a Class 8.8 set screw, in this case, bolt, whatever. You might think of it as a bolt. The only difference is the thread goes all the way to the head with a set screw. Okay, they're the same thing. Now, I have this bad habit of calling this a grade 8.8 bolt, and that's just because I'm an old fart, and when I was working in workshops, there were more graded fasteners than class fasteners. The class thing tends to be a metric thing, and the grade thing is an imperial thing. Okay, so apologies if I say that down the track. In the metric world here in Australia, it's a class 8.8 fastener. And the more common kind for use in automotive applications is a class 10.9, nearly said grade then. It's a class 10.9 fastener, and you can go up to 12.9. I've got a bunch of M12 12.9 socket head cap screws that I'm using for a project right now, just under the desk here at the Fat Cave. So they're all good but different. Okay, and I just chose 12.9 because it was the one I could get on lockdown. It was, you know, click and collect kind of thing. So I could have used any of those. It would have been sufficiently strong for the application. And in many cases, this is the case. They use 10.9 for automotive things like wheel studs and tow bar bolts because those fasteners are a little bit more durable than the 12.9s, and they're a little bit stronger than the 8.8, so they can save a little bit of weight and get a little bit more mechanical forgiveness than you get with a 12.9. So if you can see these numbers properly, a grade class 8.8 fastener has a yield strength of 640. Now, it's a big number, and it's in a thing called megapascals, which nobody can relate to, and I get that, but it's just a number. Look at it like a relative number. And if you want to contextualize it, it's 1 Newton per square millimetre. Okay, 1 megapascal is 1 Newton of force, pressure, whatever, stress, over 1 square millimetre of area. So a tiny little area like that, and 1 Newton, which is about 100 grams. Okay, 640 megapascals of yield versus 800 for ultimate tensile strength. So just think about it like this. On the way to breaking this thing, the landmarks are at an altitude of 640 for yield and 800 for ultimate tensile strength. With a 10.9, you're going from 640 to 940. So you're almost getting another 50% on the yield stress. It's a much steeper mountain with 10.9, and you're getting 1,040 versus 800. So you're only getting about 25% more, ballpark, worth of ultimate tensile strength. And that means the elevation between this peak on the way up and the summit of the mountain is shrinking. It's higher, but the difference between the two is shrinking. Okay? And when you go to 12.9, it's 1,100 for the yield. So it's almost, but not quite double the class 8.8 fastener, nearly said grade again, and it's 1,220 on the UTS, which is about 50% more. Once again, the elevation is higher, but the distinction between the peaks is tighter, okay? So it's, if you want to excuse the French, it's easier to fuck this up than it is to fuck that up. And it's pretty hard to fuck the middle one up, which is often why they use it in automotive. Now, if you're wondering about the numbers, because some people are number geeks, I mean, I'm a number geek, and if you look at class X.Y, the X is just 1% of the ultimate tensile strength. So 1% of 800 is 8, and that is the first 8 there, okay? And 1% of 1,040 is 10.4, and if we round it, it's 10, okay? So that's the 10, and that's the 12 for 12.9. And the second number's a little harder to get your head around, but it's just 10 times the ratio between the yield strength and the ultimate tensile strength. So if you get 10 times 11 on 12.2, you get 9. That's how this works. And if you get 10 times 940 on 1040, you get 9. And if you get 640 on 800 times 10, you get the second 8 there. Okay, that's just how this works. Now, I'm going to read you some stuff from the Ajax manual, so you need to wrap your brain around that. But the 3 key points here, apart from knowing that we're about to climb this mountain, but we're only going to go to a safe altitude here to retighten our tow bars or whatever else, okay? The finish of the bolts and their condition really matters. So if you've got an old and busted, rusted up bolt, it's going to perform differently during tightening than if you've got a brand new zinc plated bolt with a little bit of light oil on it straight out of the production line. Okay, that stands to reason. They'll just tighten up differently because of friction between the thread faces as they interact with one another and the mating faces of whatever you're tightening, okay? And the other thing that matters is the lubrication state, obviously. And finally, I want to get you to wrap your brain around one super important thing, which is tightening a bolt up with a torque wrench. So this is a torque wrench. If you haven't seen one, it's just adjustable. You've got this handle at the bottom, you undo the lock nut, and you can screw this bottom bit up. It's got a vernier scale on the bottom, and you can get whatever torque setting you want. Okay, and then you lock it off, and you go out and you tighten up the bolts, and when you get to the preset tension, it clicks and kind of freewheels. And even a politician could feel it, okay? It's that obvious. So that's how you do it. But there's a big difference between assembling something and then doing the last bit of the assembly, like the way I would do anything like a tow bar or wheel studs or anything of that nature, is I'd just get them sort of a little bit beyond finger tight with a wrench, okay, socket, whatever, and then I would go around and torque them up finally. All right, and there's a big difference between doing that and going and checking a bolt that is already in place. And that's because there's a difference between the surface interaction of two surfaces that are moving relative to one another, called loosely, let's call it kinetic friction, and two surfaces that are static relative to one another, and let's call that static friction, okay? And you felt this, okay? You felt it if you've ever had to slide something heavy across the carpet. It's harder to get going than it is to keep it going. It seems like you need to give it a good push to get it going, and then to keep it going at a constant speed down the hall or something, then it doesn't take that much of a push. It's certainly not as hard as it was to get it going in the first place. And that's because kinetic friction when it's moving is lower than static friction when it's stopped. And the same thing happens with bolts. So if they didn't tighten the bolts up properly, and let's say the assembly torque is meant to be, I don't know, pulling a number out of my ass, 80 Newton meters, all right? They might have only got it to 60, a particular bolt. And then you set your torque wrench to 80 and you go, and it goes click, and you think, oh, that's good enough. It may well not be, because the static torque is different to the kinetic torque, all right? So the safe way to do this is to release the fastener just a little bit. It only has to be like half a turn, quarter of a turn, just so the tension comes off, and then tighten it back up to the desired torque. Otherwise, you might think tight enough, and it actually might not be. So hold that thought. So basically what I got here is a plan. It's like a functional specification for how you should check and tech the bolts on anything. Try talking for half an hour without fucking up. It's a living hell. Anyway, this is like a roadmap about how to do this, like A, then B, then C, then D. But I just want to get some of the technicalities out of the way from our good friends at Ajax, okay? Ajax Fastener Manual and the NASA thing, link in the description. Download them. They're awesome resources. The Ajax one in particular is very useful when it comes to designing bolted joints and knowing the assembly torques for different fasteners. Okay, so the first thing I'd say here, and actually it's not me saying it, it's Ajax saying it, is this. Ajax goes, although torque bears no fixed relationship to fastener tension, the use of torque wrenches is the most common method of preload control, they mean tensioning the bolt, because of simplicity and relative economy. Many factors, including surface texture, cut or rolled threads, surface coatings, lubrication, thread interference, and speed of tightening, affect the torque-tension relationship and are up to plus or minus 25% variation in preload has been measured on similar fasteners receiving identical torque. And for this reason, I'd say consistency is really important. Speed of tightening, okay, really important. And lubrication state of the bolts, because if half of them have been lubed and the other half hasn't, then same torque's going to mean different stretch, because you have to overcome the friction between the mating faces and the threads. That's the majority of what goes into that torque on the torque wrench. And obviously, if you lubricate the thing, then that makes a real difference. And for this reason, okay, I'd suggest the mighty Copper Eze. Okay, I don't know if you can see inside here, but it's really just grease with a whole bunch of copper filings inside it. You can probably see that there. There's nothing particularly special about it, although it does make things much easier to undo over time, like if you've got to get the tow bar or whatever off your car in 3 or 4 or 5 years' time, something, then this makes it much easier, but it also makes the tightening process much more consistent. I'll try and find some of this stuff for you so that you can get it delivered in this challenging time, and I'll put a link to that in the description if I'm successful. So Ajax goes on, and this is kind of interesting too if you've got your hands on the tools, right? And like, this is what you've got to know before you rush out and grab the spanner. The purpose of controlling the torque applied to a fastener assembly is to induce a desired level of tensile force in the bolt, which is what I said earlier. Stretch equals clamping force. That's what they're saying. Unless limited by some characteristic of the joint, e.g. a soft gasket, not too much of a problem there with tow bars, bit more of a problem there on an oil or gas pipeline. Lots of gaskets in the flanges, right? The amount of tension aimed for in general engineering practice is 65 to 75% of the minimum elastic capacity, they call that the proof load, of the bolt. By selecting bolts such that this level of tension is not exceeded by service load on the joint, loosening of the nut should not be a problem in most applications. Nylock or cone lock nuts are recommended for joints where such pre-tensioning is not applicable, and as an added insurance against loss of the nut should the initial pre-tension be lost. Okay, so let's be really clear on this. Nylock nuts and things of that nature are just there to stop the whole thing flying apart. Once the nut has come loose for whatever reason, the high tensile joint is not functioning in the manner in which it was designed to function. So in a sense, it's already failed, all right? The nylock nut just stops the nut being lost and the whole assembly going out there on the road. Hopefully it buys you enough time so that you can inspect whatever before it fails catastrophically. That's what they're talking about here. They go on to say that the 65 to 75% of proof load level of pre-tension, right? So that means the assembly torque is about 65 to 75% of that proof load, which we discussed earlier. This is really conservative, okay? And that is sufficiently conservative, they say, to give reasonable, reliable torque-controlled tightening with indefinite reusability of the assembly. So if you stick to the guidelines, you're not going to wear out your fasteners, and you'll be able to adjust them and tweak them and disassemble and repaint and do whatever, okay? And it's not going to compromise the fasteners. They go on to say for critical applications, closer control or calibration checking is recommended. And they say because friction is the major unknown variable affecting the relationship between torque applied and tension induced, the presence of light oil lubrication is the minimum standard recommended for consistency in controlled tightening of fasteners, right? That means light oil lubrication. Okay, like the way fasteners come in the box from the engineering supplier. That's what the tables reference. Okay, now if you heavily apply grease or you smear a bunch of this on, you have to fudge it, right? And the recommended fudge is to take about a third away. Let's go on. Most plain finished fasteners are supplied with a sufficient oil residue from their processing, but plated finishes will generally require oiling or adjustment to the torque recommended in Ajax Fasteners technical data. So if you download this manual and stick with the recommended torque, that means if the bolt's old and rusted or something, just clean it up with a wire brush and then give it a spray of WD and wipe off any gross excess, and that will get you to that minimum lightly oiled state that will be compatible with the numbers in the table. All right, and then if you use the mighty Copper Eze, then just knock a third off, because that's what they call heavily lubricated, right? And they go on and say that in the manual if you read all of that stuff. They say, for bolts with special surface finishes or assembled with anti-seize compounds or heavily greased, the torque-induced preload relationship is likely to be altered and the recommendations to require modification. Okay? And that means knock a third off. They say that elsewhere in the manual. And lastly, I'd suggest the zinc plating of bolts, and I don't have one handy here, but I'm not talking about galvanisation, like hot dip galvanisation like you would use on a construction site for bolts that go through bits of treated pine or something. I'm talking about that shinier zinc plated finish. They say in recent tests of bright zinc plated parts, the tension at a given torque was found to progressively reduce by 50% over 5 tightenings of an unlubricated assembly, while a well-lubricated assembly showed no reduction over 5 retightenings and only a 9% reduction over 12 retightenings. And this is, of course, the other really good reason here for doing the whole anti-seize thing, because you don't want your 5th assembly to be the same torque on the torque wrench, but actually much less stretch on the bolt, just because the zinc plating of the bolts has been interfered with by being spalled or smeared away by preceding tightening events, okay? This is kind of important. So with all of this stuff in mind, let's just go through the roadmap of how you should go out there and actually approach tightening something critical like your tow bar, or just condition checking it, right? Because did the dealership check when the dealership said, in the service receipt, when they said check all chassis bolts for tightness and tighten if necessary, did they check, was there someone with a bone through his nose listening to Marilyn Manson instead? Like, I don't know. And on that subject, I'd suggest that it is kind of fun, I guess, to be on lockdown playing a bit of Uncle Cracker or Kid Rock, Marilyn Manson, whatever, all the classics. And also maybe having a beer out of the fridge, whatever. But I'd suggest if you're going to do something that matters, that's got a safety dimension, inclusive of using a power tool or bolting something up that really matters, mind on the job, you know, really important. And that would be a prerequisite. Treat the fat cave job like that more like a workplace and less like just goofing off away from your family, you know. Just to be completely, unequivocally crystal clear on this, if you're looking at an M12 fastener and it's a class 10.9, which is the most common likelihood with the bolts holding on tow bars and also wheel studs in automotive applications, okay? If you look at the Ajax table for that fastener, it says that the recommended assembly torque is 109 Newton meters. And just to take all the ambiguity out of the equation in the context of lightly oiled versus zinc finishes versus this and that, what I would be doing is just going with the Copper Eze, which qualifies as a heavily greased kind of finish. I'd be putting a light smear of this on the threads, and I'd be putting a light smear of this under the nut if possible, if it's not a captive nut, and under the head of the bolt as well. And then I'd be tightening it up to 70% of the recommended assembly torque, which is 70% of 109 Newton meters in this case is 76 Newton meters, all right? And if you're going, what is that? And you don't have a torque wrench, then you probably got one of these. Now, it's a double-ended ring spanner, okay? It's 250 millimeters long or 10 inches, America. And basically what you're looking at there is 45 kilos on the end of this wrench for the full 109 Newton meters. And then once we fudge it by the 70%, we're talking about 30 kilos roughly on the end of this wrench. Now 30 kilos up there lying on your back like this, it's a hefty pull, all right? It's very difficult to over-torque an M12 10.9 fastener with one of these babies, which is why, of course, your average torque wrench is so much longer, okay? It's like nearly twice as long in terms of its effective length, and that is merely because from a neuromuscular point of view, it requires less load to deliver the same torque, and less load is easier to deliver with some consistency when you're lying on your back out of position up there like that. And essentially that's how I would do this, just to remove all ambiguity about surface considerations and things like how many times has that zinc plated fastener been apart and how much reduction in tension do I need to allow for because it's been apart 3 times or 12 times or whatever. Just use a bit of Copper Eze and do it that way. Knock 30% off, or roughly a third, because we're only talking about going to some approximate point on the ascent to this minor summit, right? So if we're at base camp, we're only going halfway up to camp 1, and it doesn't matter if we get to here or there, but it kind of matters that we stay in this region, because this is a conservative engineering philosophy designed to avert disaster, so you don't run out of air by going too high. You're always going to be down here as long as you play it like that. So here's how I would approach this, right? You've got to identify the class of the bolt. That's absolutely critical to getting the tension right. And it's embossed on the head, so how hard is this? And then I would identify the finish and the condition. And I'd suggest that the greatest hedge there of all time is just get whatever the finish is, whatever the condition is, clean it up with a wire brush if it's in bad condition. Whatever the finish is, use a bit of Copper Eze, okay? Put it on the threads at a minimum, and then go to 70% of the recommended assembly torque in the Ajax manual, okay? Download it from the link in the description. It's important to get this right. So 70% with Copper Eze, and you are going to be in the zone in my view, okay? And then just determine the assembly torque out of the table. Look for whatever it is. Measure the diameter of the threads if you want. Metric system's dead easy. If it's about 12, it's M12. If it's about 10, it's M10. All you need is a ruler to do that. You don't need any special engineering tools. And then loosen it first to overcome the limitations of static friction, okay? Knock it back a quarter of a turn, half a turn, whatever, just so it's demonstrably loose, okay? If you're going to put the Copper Eze on for the first time, obviously you're going to have to disassemble the whole thing anyway, so you'll be assembling it in a kinetic way, but the torque is meant to go with kinetic assembly, like moving assembly, not just a static check. Then I'd be setting the torque wrench, and the torque wrench is easy to set once you figure it out, but most torque wrenches are, I don't know if you can see this properly, but most torque wrenches are in Newton meters and foot pounds, right? So you've got your foot pounds and your Newton meter scale, and you've got the one vernier. Okay, and that can be a little confusing, because if it was just in, let's say, Newton meters, the units would be easier to be 10, 20, 30, 40, whatever. It'd go up in increments like that. And in this case, it goes up in twos, okay? Because that was the only way they could get the two different scales to work using the one mechanical vernier. So if there's any ambiguity about that and you can't figure it out, get someone who knows and get them to show you, okay? Because getting this wrong is not acceptable. And the other thing I'd tell you about using a torque wrench is that it's a good idea to start with it backed off and tighten up, as opposed to overshooting and then coming back, because there's always a bit of play in machine type threads. And if you're on the way back, it's a different thing to being on the way up, okay? So maintain consistency by doing it on the way up from an unloosened state initially, and then lock it off with this nut. And from time to time, just check it. And don't treat this like it's a hammer or just a normal wrench. Like, use it for its intended purpose, okay? So you set the torque wrench, and then I'd be tightening it up systematically, which means I'd be flipping Marilyn Manson off, and I wouldn't be doing it down the bottom of the 4th or 5th beer, or even the first one, because it's too easy to fuck this up. Okay, and I'd further suggest, I always get this question, does it matter if I tighten the bolt or the nut? And the answer is no, it doesn't. With a lot of things like toe bar installations, not so much the toe ball, okay? With toe bar installations, particularly bolts that are going into tube chassis, they're often going into what they call captive nuts, which are nuts welded on the inside of the chassis, or nuts welded onto a plate that you slip into the inside of the chassis. So it is impossible in any case to tighten up those kinds of nuts, and you will be tightening up the bolt. The only problem with tightening the bolt is that if there's substantial load, like shearing load, on the bolt itself. So if you've got something pressing down onto the shaft of the bolt, pressing down hard, it can require additional torque to overcome that. This should not be a factor with things like tow bar assembly, the loads during tow bar assembly for misalignment and gravity pulling the bar down. They're not significant enough to have an effect, but it could be substantial if you're tightening something up that weighs several tons, like a big piece of pipe or something. And if you're doing that, then you should use jacks or cranes or other mechanisms just to take the preload in shear off the bolt. And once it's tightened up, it shouldn't be carrying any load in shear in any case. So I'd be tightening that up systematically. Tightening the head of the bolt is fine, dude, especially when it's the only option when you're using a captive nut. And then, really important because of human fallibility, I'd be double checking every one. And you don't need to compensate for the static friction there. You just need to go around every bolt again with the torque wrench and just make sure that it clicks. And that way you will know beyond reasonable doubt that you have not left a bolt loose, because that's kind of a disaster, because the dude who spent forever designing the bloody thing did not make allowances for somebody only tightening up every 3 out of 4 bolts. You know what I mean? Like, every one is kind of important. And the final thing, which is really important, is that you've got to condition monitor anything. And in a sense, that's why you take your car in and have it serviced, because they're supposed to check those bolts and they're supposed to check everything else like that. And if you want to take responsibility for something like tightening up a tow bar, where if you get it monumentally wrong, there is a catastrophic failure in the offing. The chance is low, but it's there, okay? So you must take responsibility for this stuff. You don't just tighten the bolts up and then walk away for infinity. What you've got to say is, let's see what happens in a week, and just go over it again with the torque wrench. And you don't have to compensate for kinetic versus static friction. Just go over it with the torque wrench again and go click. And then you'll know that nothing has come particularly loose. And then wait another 3 weeks and a month after the first go at it, just have another crack at those bolts. And then that's looking pretty good. And obviously, if you're going to go out and use, say, a tow bar for the very first time, you hook up a heavy van or a trailer with all your tools in it or something like that, it's a brand new tow bar, then you'd be checking the bar before you go for a drive, and then after 24 hours in service, I'd be checking those bolts again. And then at some other point down the track after towing, maybe a week down the track, if the first day's going okay, then a week is looking good, you know, and then a month might be appropriate. And after that, you will have a roadmap in your head about the integrity of that installation. And it's probably not going to be a problem for the next 12 months. And that way you could do a check every time you service the car, or you could just check these things, I don't know, you could check them on the first day of summer and the first day of winter, whatever. Just have a reasonable interval for checking this stuff. And if you approached everything like that, you would be, frankly, so much more professional and so much better insured than, and I mean insured not in the context of an insurance policy that you pay for, but real insurance. Like, this stuff is insurance, that you don't have a disaster. So it really matters. And if you did this in a diligent sort of organized way, and you put it in your diary, and 6 months down the track, I'm going to check this, you know, and a whole bunch of other things as well. You could have that day is vehicle once over day for Fred or whatever, then you'll be so much better insured and so much more professional and diligent than the ambient level of servicing going on out there in society today.